So again, the lecture agenda, we're going to finish off chapter 7 looking at valence electrons, ions, and particularly the electron configuration of ions, which are very predictable. And then periodic properties. There's a whole bunch of kind of trends you can look at just from analyzing the periodic table. And then finally, just a little bit of looking ahead. This looking ahead, looking at types of bonds, electronegativity, and covalent bonding, this is all preparing us for Lewis structures, which is something we're going to work on when we come back after the test, right? So that's kind of the idea for that. Okay, so let's talk about valence electrons. So valence electrons are electrons that are in the highest, we should say occupied energy level. And so when I'm talking about energy level, not to be confused with the sub-level, I'm specifically talking about the total highest N value or principal quantum number energy level. And this is what's found in the ground state. There's kind of a shortcut for this as well. Well, let's do an example first. So sodium is 1s2, 2s2, 2p6, 3s1. What's the highest N here that I see? Anybody?
3s1.
Yeah, so I'm just going to say 3 equals the highest. And how many electrons?
1.
1 electron.
Yeah.
So sodium has 1 valence electron, right? Actually, we'll see later on. And we wrote this also, by the way, as sodium neon 3s1, right? That the condensed electron configuration separates out for the most part, not entirely. There's some exceptions, but like the intervening D. But in general, the noble gas configuration, the condensed electron configuration, fetters out that valence electron. And we can later on see sodium's given a dot, just a single dot. This is called the Lewis dot. There's kind of a simple way for doing this, especially for main group elements. For main group, which was main group again?
1A through 8A.
Perfect. So the 1A to 8A, for main group, the number of valence electrons is equal to the group number, right? So if I'm in the 1A, it's always S1, whatever it is, which is 1 valence electron, right? So sodium is 3s1. Lithium would be 2s1, right? And so on. Potassium would be 4s1. For the 2A, it's always S2, or 2 valence electrons. For the 3A, it's always S2P1. Well, maybe we should look at a periodic table briefly for a sec here, just to remind ourselves. So when we look at this, so these guys, so again, S1S1, 2S1, 3S1, 4S1. There is no, the only exception to this, by the way, would be helium, which is 1s2 over in 8A. but the rest of these would be 2s2 for beryllium, 3s2 for magnesium, so on. When we get to boron, it's 2s2, 2p1. So the 3a are always have 3 valence electrons with an s2p1. The 4a are s2p2 with 4 electrons. 5a, kind of see this pattern going, s2p3, 5. 6a, s2p4, 6. I guess I'll go over here. The 7a are S2, P5, and then finally the 8A are S2, P6, except helium. All right. And so this also works if I have an intervening d orbital. So let's practice some of these. What about, let's look at, actually, well, okay. How about silicon? Let me bring that up higher. Silicon would have how many valence electrons? Anybody? So which group is it in? Can you guys see that? Maybe it's hard to see. Bring the camera down, maybe.
4.
Yeah, there's 4. So it has 4 valence electrons, right? What about, here, let's do a harder one. What about bromine? Whoa. How many valence electrons does bromine have?
6.
7.
7. Yeah, so technically, if I look at bromine, bromine's kind of weird. Bromine would be argon, 4s2, 3d10, 4p5. And so what happens is, let me get a red pen or something. Blue will work. Once I fill this D group, the D goes and joins the third energy level. The D10 joins the third energy level, and it's ignored, right? Because bromine is really, if I look at bromine, it's actually 1s2, 2s2, 2p6, 3s2, 3p6, and then the 3d10 joins with the third energy level, 3d10, right? And then I have 4s2, 4p5. So it's still and this works for if I'm adding or removing electrons, it's going to do the same kind of thing. That these electrons reactive. That this is now the new core, right? The core electrons were argon. Actually, we should define that too. So we have the valence electrons, again, are the outermost n electrons. And then this is looking at versus the core electrons. The core electrons are all n electrons besides the outermost n electrons. So again, in the sodium, which was 1s2, 2s2, 2p6, 3s1, there's 10 core electrons, and there's 1 valence electron. And the core electrons are very unreactive. Whereas the valence electrons are reactive, meaning they can be gained or lost. And usually they're gained or lost to form an octet. Okay. So let's see if I can, I'm going to go to the PowerPoint for a sec so we could practice this a little bit. I think that might be cool. Let's try. So if we can leave the camera and go to the, did I do it? Share. Why is it not showing green? Okay, where's the green circle? Can you guys see the broader screen right now?
Yeah.
Okay, perfect. So let's pull up just a little reiterization of the valence electrons. So the last filled principal energy level is called the valence level or the valence shell. The valence shell contains electrons that are highest in energy and occupy orbitals that extend further from the nucleus than those in the lower levels. The valence electrons occupy orbitals in the valence level. All other electrons are called core electrons or inner electrons. So with bromine, we saw that we did this one, right? We have, we look at the 4s. So let me annotate here. Gosh. Let's do text. So the N equals 4 is the highest. And so that all those are valence. And if I look at them, it's an S2P5. So there's 7 electrons in the valence. Okay, and that's basically what's being shown down below. Okay. Okay. What about fluorine? I guess you'll have to look at your periodic table in order to do that. Or we could do the electron configuration really quickly, which is 1s2, 2s2, 2p5. How many valence electrons does fluorine have?
5.
Well, I'm going to count the S and the P actually. Count the S. So it's just the so it's the high. Let's make a little note for ourselves. It's a good thing we're practicing. So it's the highest N, including all sublevels. So in this case, it would be the S and the P. So we have 7 valence. Let's try another one. Let's go to, so I can. Okay, 7. There we go. 7 valence. What about lithium? So lithium is, maybe I should move the text box over here so this is getting in the way. It's 1s2, 2s1. How many valence electrons?
3.
Oh, well, okay, careful. What's the highest? What's the highest N value?
1, 2.
So the highest N equals, oh, did I get it? Equals 2. How many electrons are in the 2?
The 1.
1 electron.
Oh, okay, okay. Okay, I get it.
Not so bad. Not so bad. Okay, so just click. So 1 for lithium. How about sodium? Sodium is 1s2, oops, 2s2, 2p6, 3s1. So 1 electron. Oops. So let's go back to mouse. Click. Yep. carbon. What's carbon? I have to go back and do the electron. 1s2, 2s2, 2p, oops, 2. How many valence for carbon?
4.
4, right? Absolutely. Silicon, ooh, it's in the same family. It's right below carbon. What's it going to be?
4.
Yeah, it's also 4. So that would be, what would that be? That would be, it's actually, it would be neon. Let me put that in brackets. Brackets, neon. Oops. And 3s2, 3p2. Yeah? It's just one period below. Okay. What else? Is that it? Oh, lead. Ooh, that's a tricky one. What's lead going to be? You guys look at where lead is?
Yeah.
So lead's kind of complex. That one has a really hard electron configuration. It's the noble gas before lead is xenon. And then what comes after xenon? 6s2. And then I go 5d1, and then I finish the 4f14. So I go 4f14. This is kind of crazy, huh? And then I go back and I finish the 5d. I get 5d10, and then 6p2. So how many valence electrons? What's the highest n?
6p.
The highest n equals 6. What's that? How many have 6?
2.
I have S2 and P2. So that equals 4, right? It's technically 6s2, 6p2. So when lead reacts, it's no mistake. I'm echoing here, sorry. It's no mistake that lead can be 2+, or lead can be 4+, which is removing these outer. So lead 2+ removes the 2p electrons. Lead 4+ removes the 6p2 and the 6s2, right? So that's the deal with lead. Yeah. Okay. So that's figuring out valence electrons. So it still follows that pattern of, you know, lead is in the 4A. All D, E, and F. Let me do another text. These are all 4A, right? So they all have 4 valence electrons. So we just did a complicated look at it, but it's still in the 4A, and so it follows this pattern. Yeah. Okay. So elements in the same group have the same number of valence electrons. That's kind of the take-home message. It's really handy. Okay, let's continue. Let's some practice. Okay. Valence electrons. So you guys probably have a periodic table in front of you, maybe. How many for magnesium? It's element number 12.
12.
Well, it doesn't have, it's element number 12, but it doesn't have 12 valence electrons. How many does it have? So you have to go to, what group is magnesium in?
2A.
It's in the 2A. So how many valence electrons then?
2.
2. All right, perfect. Group 2A, 2 valence electrons. What's next? Carbon. What group is it in?
6A.
Nope. 4A.
Oh, yeah.
So it would have 4
Four.
valence electrons. Group 4A. Okay. Or 14 is that's the other system. I like the A and B. That's what I've taught throughout the class. What about boron? What group is boron in? Element number 5.
3.
It's in the group 3A, so it has
3 valence.
3 valence electrons, an S2P1, right? Carbon's an S2P2. Magnesium's just an S2. Chlorine. Okay, that's element number 17. What group is it in?
7.
7. So how many valence electrons?
7.
It's pretty, that's not bad, huh?
Mm-mm.
Selenium is in, element number 34. What group is that in?
6A.
6A. So therefore,
6.
6. So that should be, if I put a test question like that, hopefully that would be an easy question. How many valence electrons are in carbon? That would be or selenium or whatever. That would be a pretty, the harder ones, like, well, selenium technically has, let's do a text box for selenium. Technically, it has a, well, let's see. Selenium has argon, whoops, let's see brackets, argon, whoops, and 4s2, 3d10, 4p, selenium was 4p4, right? So it has that intervening d orbital, but you still, at the end of the day, you just group, it's s2p4. That 3d10 joins the third energy level, right? So it becomes unreactive once it's filled. I have 10 minutes. I think we're doing good. You guys, will someone let me know when I have a minute left? Is that cool?
Yeah.
Get chatting away. Okay. Oh, mouse. Oh, come on. All right. So there we are. All right. So let's continue. All right. Electron configurations for ions. Let me erase that little thing down there. In atoms, the number of electrons is equal to the number of protons, which is the atomic number. We know that. So like carbon's element number 6. So how many protons does carbon have? Carbon is element 6. So 6 protons. And then how many electrons then?
6 electrons.
6 electrons. All right. For ions, the electrons does not equal the atomic number. So for ions, let's put a text box down here. So for ions, the number of electrons changes. Either we gain or lose electrons, right? So write the electron configuration for the potassium ion or the oxide ion. So can we do that? Let me go further. Mouse. Okay, so we did, okay, so let's do sodium. What's the electron configuration for sodium? Sodium is brackets neon, oops, 3s1. It's no surprise that sodium only goes +1. It gets a plus, right? So what does plus mean? What does a plus charge mean?
Lost an electron?
Yeah, lost 1 electron. Which one am I going to take away?
3s1?
Yeah, I'm going to take away the 3s1. So sodium, its electron configuration becomes neon, or sodium plus, excuse me. Let me put the plus there to emphasize. Becomes neon, right? Or if you want, 1s2, yeah, 2s2, 2p6, right? And so a lot of main group elements get noble gas configuration as an ion. Did I have more room? Let's put more room. As as an ion. Okay, so write the electron configuration of sodium. So there we go. We just remove one electron. What about bromine?
Gained one.
Yeah, it gained one. So what would it be? Let's see. So bromine, how many valence electrons does bromine have? So bromine is an S2. Bromine's in the 7A, so it has 7 valence, which is an S2P5. And then what we do is we gain one.
P6.
Gain one to become, yeah, S2P6. So then bromine just becomes, we just added one to it. So it was, before, it was 4s2, 3d10, 4p5, but now it gets to be krypton. It gets this noble gas configuration. What about nitride? So let's try again. For nitride, what's nitrogen? Nitrogen is got 7 electrons.
5A, yeah.
1s2, 2s2, 2p3. And if I gain 3, what am I going to be? Someone said it. I'm sorry, I cut you off probably.
Neon.
Neon. Yeah, N3 minus equals neon. That's what we'll see, sure. There we go, neon. What about potassium? So potassium was, what was it? It was argon, darn it, 4s1. Oops. Equals potassium. So potassium plus equals, should be pretty easy, huh?
Argon.
Argon.
So you go backwards as well.
Yeah, so the metals lose an electron. They go backwards. Maybe we should show that in a second. The metals go backwards to get noble gas. The non-metals as anions gain electrons to become noble gas. That's exactly right. Right. Oh, strontium, element number 38. Look at your periodic table. What happens to it? What's strontium going to do? It's going to lose 2 electrons, so it'll become 36. What will it get? What's element number 36? Krypton, right? And so on. So these patterns, actually, we were asked to learn these before. Remember, the 1A is always +1, the 2A is always +2. The 5A as an ion is -3. The 6A as an ion is -2. The 7A as an ion is -1. Noble gases, of course, what are noble gases going to do? Anybody? Noble gases.
It's going to stay the same.
It's going to stay the same. It's actually really hard to get a noble gas to react. You have to really coax it into reacting with anything at all. In nature, it doesn't react. All right. Well, sulfide 2-. So let's do that one. I might as well while we're at it. So sulfide, sulfur is 1s2, 2s2, 2p4. So S2- whoops, would then be what?
Sp2p6.
Yeah, which would be
Argon.
Well, actually, that would be 10 electrons, which would be neon. But yeah, you got the point of it being a noble gas, right? That's the main idea. Wait, what happened? Did I do that wrong? Oh, I did do that wrong. I'm sorry.
Yeah.
No, yeah.
I was doing oxygen.
Yeah, you were doing oxygen.
I was doing oxygen. Oh my gosh, Mr. Canton. Okay, let's erase that. Whoopsie. Anyway, So nickel's interesting. Let me actually talk about that because I don't think the PowerPoint does. Actually, nickel's a transition metal. What the heck happened? Aha. That might be different. Okay. So, and they just skip that. So I want to talk about it just for a second. Let's erase this. And I'm going to go back to paper, if you guys don't mind. Oh, I have less than a minute. So this might be a good place to actually jump out because it's a new idea.
Alright.
Is that okay?
Yeah.
Okay, I'm gonna end here. We'll come back.
Okay.